And this is the title of my talk, quantum simulation of Dirac-Farman mode, Majorana-Farman mode, and the Majorana-Weil-Farman mode in the cavity QED lattice. And my name and affiliation and the acknowledgement in the Raman Research Library to helping me a lot in my research. And the reference of the talk is this, actually part, only the final result I can emphasize on it. Okay, and the few important reference, I have learned this subject from the first reference, and the last one, it may be help the student and postdoc. I have done the detailed derivation of the subject as a mathematical physics. Okay, then next talk, the outline of the talk. At first, I would like to state the what is quantum simulation, why the quantum simulation for the relativistic physics is so important, and then the why the interacting light matter system as a quantum simulator. And the fourth part is the condition for the Dirac-Farman mode, condition for the Majorana-Farman mode, condition for the Majorana-Weil-Farman mode, and then you know the E-type chain, the topological state of the matter has come from the E-type chain, how I can quantum simulate the E-type chain in the interacting light matter physics, or in other words, I can say it optical E-type chain. Finally, the conclusion one. Then what is the, I don't know, in my app talk, it looks so nice and big, but why it is so small, I'm not able to understand it. Sorry, but still I express my sorry to everybody. Okay, what is the quantum simulation? In quantum simulation, one aim is to simulate a quantum system using a controllable laboratory system that underline the same mathematical methods. That therefore it is possible to simulate a quantum system that can be neither efficiently simulated on a classical computer or the easily accessible experimentally. In the due course of my talk, you will find that I here quantum simulate mathematically of the relativistic physics by using the cavity QED lattice. By using the cavity QED lattice, I can get the all relativistic physics like the Dirac-Farman mode, Majorana-Farman mode, Weil-Farman mode, and the crossover from the one Farman to the other mode also. Okay, so like now the why I'm so much interested in the quantum simulation of the relativistic physics. In the relativistic physics, it is very hard sometimes to simulate in the experimentally in the accessible facility. The thing is this difficulty of this this type of harmonic mode, different kind of harmonic mode, and their crossover from one to other, I can simulate in the interacting light matter physics, also in many quantum condensed matter system physics. Sorry, the quantum simulation is this. You kindly see there are different kind of quantum condensed matter physics, or in the other, I can simulate in a 1D or 2D lattice in terms of the qubit physics. Okay. My goal is this here, the other, that is a relativistic physics in terms of interacting light matter physics, I can say, and why I am interested in the interacting light matter system as a quantum simulator. Actually, the thing is this, if anyone know, the Sergei Haros has done last 30 to 35 years to develop this subject. He has developed the subject in such a way when he started in his career almost 5 years, there is a factor in this field called the cooperative factor, Azar as a xi, the Azar of the two ratios. At the starting point, it is only few tens only. Now this factor is of the order of 10 to the power 6 to 10 to the power 9 for the precise measurement of the quantum states. And at the same time, the interacting light matter physics, the basic particles are the photon. And their experiments are almost in the state of art, and or in other words, I can say those experimentalists of the cavity QED lattice or in the interacting light matter system, almost the god of small things. If you do any calculation in your exercise book and tell them, look, in this field I have done in this, emit this result, this calculation, this phase, those experimentalists can do this experiment to find your phase in their experiment. The experiments are so efficient in this case. Now the thing is this, I have been already told that my goal is to find So it is needless to say again that is the goal of this talk. The goal of this talk is this. The thing is this the Majorana Weil-Fuhrmann mode when it is appear for the which parameter space of the cavity QD lattice. That is the Dirac-Fuhrmann mode when it is appear for the which parameter space of the cavity QD lattice. And then finally how I quantum simulate the type chain for the which parameter of the cavity QD lattice. And there is a crossover of this field from this. The model Hamiltonian of my system is consisting of the two parts, HA, HC, and HAC. What is the HA? HA, I will come to this point again. Suppose I have a single cavity, these three parameters are generally, I'm really sorry again to the open audience, but in my laptop it's so good, I can't imagine why it is coming here in this fashion. Okay, the thing is this, a single cavity. A single cavity G is the dipole moment between the atom-photon interaction, and this is the spontaneous emission rate, and this is the decay of the cavity. And see here, this is the area of the cavity, the lattice of the cavity, and there is no area inside this. And these are the photon modes. Photons are coming across these lattice sites. And here you will see that there is the atoms or the ions or the superconducting quantum dot or quantum dot spin level system of few levels, and those are interacting with the external quasar. Now again I will come to this point, HA, HC, and HAC. H is the atomic level or the superconducting qubit level or the quantum dot two or few level system. In my case, there are three atomic states, and finally the A, this is a one atomic state we would consider as an atom level 0. So the B I can consider in terms of omega B, and this is the excited state. And inside the cavity there is some electromagnetic radiation, and so this electromagnetic radiation I can write the Hamiltonian in terms of this. This is the energy of the electromagnetic radiation, and Jc is the coupling constant of the hopping of this photon across the lattice side. These are the photon creation and annihilation operator, and this is the atom-photon interaction in terms of the radiation inside the cavity, and also the external quasar field I applied in the cavity. And this omega A is the Rabi frequency oscillation, and small omega A is the frequency of this thing. So I have been already told you, and the basic Hamiltonian picture, three level state, A, B are the two level state, and finally E is the excited state. It can be eliminated by the adiabatic process consideration, and from this one can also find the effective spin model of the system. That is you see here the effective spin model is nothing but in terms of that, and also this effective spin model for the two stable state of the neighboring cavity can be found, and also I can write my Hamiltonian in terms of the system Jxy Hamiltonian, J1 and Ky. So the all coupling constant I am getting in terms of the system parameter. Now I will play how I can get the quantum phases of one of the other. My first result is the Dirac-Fuhrmann mode. I can achieve the Dirac-Fuhrmann mode in this limiting calculation, and you see the Hamiltonian after the Jordan-Wigner transformation and Abelian quotient method. I can find my Hamiltonian in terms of that, and so that Dirac Hamiltonian I can express in terms of massless, and one can express the Dirac Hamiltonian in different representation. This representation where I have written is called the covariant representation. If you write the Dirac Hamiltonian in any representation, but find it that your all gamma matrices should be satisfied the Clifford algebra. My all gamma matrices are satisfied the Clifford algebra, and now I would like to come how I can get the Majorana-Fuhrmann mode and how can get the other result. Suppose if I consider this image A1 equal to J2 my coupling constant, so in terms of the parameter space, this gives me the parameter space, and this condition is a given physical condition. You know the quantum simulation, this is the type chain of the standard TOF superconductivity for which initiated the topological state of matter study. This type chain I can achieve in this condition T equal to J1 plus J2 delta J1 and mu equal to minus 2B. And after this, if I consider this Hamiltonian in this image, I can finally recast my Hamiltonian in terms of the transversizing model. The parameter space is this. After taking the Fourier transform, I can get the one-to-one correspondence, and the detailed derivation is in my EPL paper. The thing is now if I do, there is a detailed calculation. If I consider the inner chi1n and chi2n, and then I do the detailed derivation, I saw that is the chi1n and chi2n is the dagger of itself. That is, they are satisfying the Majorana particle condition. Particle and antiparticles are equal to the same, and also these are anti-commutativity relation, that is, they are using the harmonic character in detail. And finally, after the detailed calculation, I have not mentioned the detailed calculation here. I can take the gamma matrix in this. Sorry, there is a equation for the chi in terms of this, and so I can write this equation in terms of that. So the thing is this, that you know when Dirac equation Dirac proposed in the 1928, he find the psi in terms of this scalar complex quantity. Majorana started to find how he will, sorry, I beg pardon. But the Majorana started to write down one more Dirac equation where the particle and antiparticle will be the same, and he expressed in terms of that. So whether that the particle and antiparticle satisfy the gamma matrix, satisfy, that is the imaginary term, and you see this, then this the chi is the EL value, and for this case you will find the Majorana Weil-Farman mode. I can consider the case when m equal to 0, that is lambda equal to 1. In terms of the cavity QUD, at least this is the parameter I must be found, and it's a physical parameter. And finally the conclusion, and that is a mistake. The conclusion is this: there is in this short talk or in this work I have quantum mechanically simulate, there is the relativistic physics, particularly the three particle, Dirac particle, and the Weil-Farman particle, and the Majorana particle, and the crossover among them, underplaying the parameter space of the interacting light matter physics from the perspective of the quantum simulation. Okay, thank you again for your kind attention.
Any questions?
Sorry. Are the local modes in your cavity the spins or the fermions?
Okay, very good question. Here the local modes are the photon. Okay, photonic physics.
You form some superposition to get the spin effective of freedom. So are they local or?
Local means it is extended
local
to the
space.
Cavity. No, it is a hopping. It has a hopping, and it is extended up to the cavity lattice.
So, sorry, can I ask another question?
Yeah. Of course you ask.
Hey, you can continue.
Then, I mean, why are the Majorana modes stable, robust to perturbations? Because these are non-local modes. You can just
Majorana modes. If you I have not written this expression explicitly. If you find my paper, you will see the Majorana Farman mode in this case appears only at the edge. Only at the edge of this ability, that is not the bulk. Bulk is the gap. I have not done it only 15 minutes talk. I have not even the whole expression. Bulk is the gap, but the edge is the gapless, and the Majorana Farman mode appearing in the edge. So please see my work. Thank you.
Okay, let's thank the speaker. The next speaker.